Hi guys, welcome to the video that is going to be the class examples for videos 1 and 2. So the examples that we're going to be going through are the ones that we did not get to in class, and they are all immediately following the video 2 notes. So we're going to start with example 1. So this is, suppose that a gas phase reaction, A goes to B and B goes to A, are both elementary processes with rate constants of 3.8 times 10 to the negative second and 3.1 times 10 to the negative first, respectively. So that means that A goes to B is this 3.8 times 10 to the negative second, and this B to A is 3.1 times 10 to the negative first. So A wants to know what is the value of the equilibrium constant for the equilibrium A and B. So the first thing we need to do is figure out what K is. So we're trying to figure out what is K. And the second part wants to know which is greater, partial pressure of A or the partial pressure of B. Now, if all we are given is rate constants, we can still calculate the equilibrium constant because K is the forward rate constant divided by the reverse rate constant. So if we take the forward rate constant, which is A goes to B, which is this 3.8, and we divide it by the reverse, which is this 3.1 times 10 to the negative first, we can actually find our K. So you can find K by looking at your rate constants. So when you divide those two, you should get 0.12. Again, that's because when we are trying to find our equilibrium constant, we can divide our rate constants, so forward divided by reverse, and we can get our equilibrium constant. And then it wants to know which is greater at equilibrium, partial pressure of A or partial pressure of B. So here's where we need to look at K. And if K is less than 1, we have one side that's favored. And if K is greater than 1, we have another side that's favored. So we have 0.12, this is less than 1. So think about what it means with your equilibrium constant expression. It's always products over reactants. So if you have a small number, that means that the number on the bottom is bigger. So the number of reactants is actually larger than the number of products. So because Kc is less than 1, reactants are favored, so the partial pressure of A is greater. So example 3 says, when the following reactions come to equilibrium, does the equilibrium mixture contain mostly reactants or mostly products? So whenever we're looking at what is true at equilibrium, we have to look at the K value. If K is less than 1, our reactants are favored, and if K is greater than 1, our products are favored. So if we look at A, our Kc is 1.5 times 10 to the negative 10. So think about what that means. K equals products over reactants. Right? K is always products over reactants. So if this is a really, really, really small number, that means that your products over reactants, that means you're dividing by a bigger number. So that means that reactants are favored for part A. For part B, our Kp is 2.5 times 10 to the 9th. That's a really big number, which means when you set up K, products over reactants, your products is going to be bigger because that means that you have a bigger number on top and you're dividing by a much smaller number. And so in part B, because Kp is much greater than 1, your products are favored at equilibrium. So example 5 says at 1000 Kelvin, Kp is 1.85 for this reaction. We want to know what is the value of Kp for this reaction, so the opposite. And we want to know what is the value of Kp for this reaction, which is twice as much as the original. So essentially what we're doing is we're looking to see what we have to do to the reaction to make it look like the original. Kind of like Hess's law, except because our K expression is all with multiplying and putting things to the exponent, when we are manipulating our reactions, it's going to be a little bit different. And so the value of Kp for part A, if we're flipping it, instead of just flipping the sign, because we actually don't get negative equilibrium constants, instead of flipping the sign, write what the equilibrium constant expression would look like for A. So pause the video really quick and write what the equilibrium constant would look like for part A and compare that to what the equilibrium expression would look like for the original. So hopefully what you find is that it's actually the opposite. It's the reciprocal. So because it's the reciprocal, we actually take 1 over our Kp and we get 0.541. So when you have to flip a reaction, you actually do 1 over your K. For part B then, notice compared to the original, we're just multiplying by 2. So since we're multiplying by 2, we're not just multiplying K by 2. Instead, everything is either a reciprocal or you take it to the power. So because we multiply it by 2, we actually do 1.85 squared to the second power, and we get 3.42. So as you're looking through this, if you're like, wait a second, what? Go back into video 6.2 and rewatch that section on manipulating your K values. So example 6 says mercury 1 oxide decomposes into mercury and oxygen based on this reaction. A says write the equilibrium constant expression for this reaction in terms of partial pressures, and then explain why we normally exclude pure solids and liquids from equilibrium constant expressions. So whenever you're given a reaction, if you notice that there's a double-sided arrow, that means it's at equilibrium. That means your forward rate is equal to your reverse rate. So if we want to write the equilibrium constant expression, we need to do products over reactants. But remember that we don't include solids and liquids. Those are pure solids and liquids we don't include, which means we have Kp equals the partial pressure of O2. If it says in terms of partial pressures, that means it's Kp. And you can have Kp equals just one thing. So partial pressure of O2. That is your equilibrium constant expression. Now, when we're looking at excluding pure solids and liquids, the reason being is because the concentration or the pressure is constant for pure solids and liquids. The concentration of a pure solid or pure liquid doesn't change like gases and aqueous solutions do. So that's why we actually exclude them from our equilibrium constant expressions. So example 7 says gaseous hydrogen iodide is placed in a closed container at 425 degrees Celsius where it partially decomposes into hydrogen and iodine. And so here's our equilibrium reaction. And then it says at equilibrium, it is found that the concentration of HI is 3.53 times 10 to the negative third, H2 is 4.79 times 10 to the negative fourth, and I2 is 4.79 times 10 to the negative fourth. So notice that this says at equilibrium. That's really important. These are our concentrations at equilibrium. That saves us from a couple steps. This wants to know, what is the value of Kc at this temperature? All right, Kc means we're using concentration, so we're good because we have concentration already. So the first thing that you need to do, even if it doesn't ask you to write the equilibrium constant expression, a lot of times on free response questions, you actually get a point for having actually written the expression. So the first thing to do is write the Kc expression. So take just a second and write your Kc expression. So you should have written Kc equals the concentration of H2 times the concentration of I2 over the concentration of Hi squared, because it's products over reactants. Products over reactants. So now once we have our Kc expression, because these are the concentrations at equilibrium, we can plug these concentrations directly in. So again, because this says at equilibrium, these are the concentrations that we have once this reaction has reached equilibrium. So just plug these concentrations directly in and solve. So pause the video, plug those in, put it in your calculator, and solve for Kc. So when you plug in your concentrations, you get H2 and I2 on the top and Hi squared on the bottom. Don't forget, if you have a squared, to actually square it when you plug the numbers in. You get 0.0184 for your K. Remember, K does not have units, so K is just a number. What this K tells us, because it's less than 1, So notice this is less than 1, which means the number on the bottom here must be larger. We must have to divide by a bigger number for us to have a number that's less than 1. So we actually have more reactants at equilibrium. So example 8, the equilibrium 2NO plus Cl2 yields 2 NOCl is established at 500 Kelvin. An equilibrium mixture of the three gases has partial pressures of 0.095, 0.171, 0.28, respectively. So we have NO, Cl2, and NOCl. This wants to know, calculate Kp for this reaction. So read the question carefully because this says an equilibrium mixture of the three gases. So these are the partial pressures at equilibrium. So if we want to calculate Kp, the first thing we need to do is write the Kp expression. So what I want you guys to do is pause the video, work through this problem, and see if you get the same answer. And then go ahead and just work through the video through the solutions part. So the first thing you have to do is write the Kp expression. So Kp equals the partial pressure of NOCl, because it's always products over reactants. So NOCl squared, because of this 2 out front, over the partial pressure of NO squared times the partial pressure of Cl2. So then we plug the numbers in, 0.28 squared over 0.095 squared times 0.171. When you guys plug this in, be careful. Do this bottom part first, write down the number, do the top part, and then divide. Because a lot of times people will forget about order of operations. Or you can do in your calculator 0.28 squared divided by, and then in parentheses, 0.095 squared times 0.171 and end your parentheses, and then that will still get you the answer. And you get 51. So now think about what this K means. 51, that's greater than 1. Which means the number on top is greater. So since the number on top is greater, that means you have more products at equilibrium. If K is greater than 1, you have more products at equilibrium. Okay, so example 9 and example 10 are actually dealing with actually calculating our equilibrium concentrations from initial amounts. And so really there's 3 steps that we're going to be working through, and it's looking at the balanced equation. So if we don't have a balanced equation, you always want to write it. We're going to write and complete an ICE table. Okay, so initial, change, and equilibrium. That's what ICE stands for. And then we will write the equilibrium expression and we will solve. So example 9 says a mixture of 0.1 moles of NO and 0.05 moles of H2 and 0.1 moles of H2O is placed in a 1 liter vessel at 300 Kelvin. The following equilibrium is established. So here's our balanced equation. And we know at equilibrium, the concentration of NO is 0.062. So all we know is our initial amounts of moles and our volume. And we know at equilibrium, NO is 0.062. So the first thing it says to do is calculate the equilibrium concentrations of H2, N2, and H2O. So the first thing we need to do is figure out how much did NO change by. Because we started with 0.1 moles in 1 liter, so that's 0.1 molar. We started with 0.1 molar of NO. We end with 0.062. So when we do 0.1 minus 0.062, it is actually 0.038. It's just rounded to 0.04, but 0.038. So once we know the change in NO, we can set up what's called an ICE table. So sometimes you'll see it referred to as a RICE, R-I-C-E, because you always put the reaction on top. So we have the balanced equation. Always rewrite the balanced equation when you do an ICE table. It's very helpful. Then the I stands for initial amounts. So based on what you're given up here, put in your initial amounts. So 0.1 molar, 0.05 molar, and we have 0.1 molar H2O. The reason it's molar is because 0.1 moles divided by 1 liter. Because it doesn't say anything about N2, assume that you don't have any. So then we have to go through the change. Because we know that NO changed by 0.038, I'm going to put that in. You always use up your reactants and you make your products. So we use up 0.038 NO, 0.038 molar NO. Now, this change row deals with these coefficients. So NO to H2 is actually a 1-to-1. It's 2-to-2, which reduces to 1-to-1. So if we use up 0.038 molar NO, we also use up 0.038 molar H2. And then we look at the products. Notice H2O is also 1-to-1 with NO and H2. But because it's a product, we actually make it. So if you just remember in your change row, your reactants are always subtracted out because you use them up. Your products are always added in because you're making it. So because H2O is also 1-to-1 with NO and H2, we make 0.038 molar of H2O. And then N2 is a 1-to-2. So NO, H2, and H2O are all twice as much as N2. So we just divide this 0.038 by 2 to get our amount of N2. So 0.019 molar is how much N2 we make. And then the equilibrium row, we just go through and we just do this math. So 0.1 minus 0.038, 0.05 minus 0.038, 0 plus 0.019, and 0.1 plus 0.038. Those are equilibrium concentrations. So that's the first step that we always have to do if you're not given equilibrium concentrations. You have to actually use an ICE table and solve for the equilibrium concentrations. So once you have the equilibrium concentrations, we can then calculate Kc. We can calculate the equilibrium constant expression. So for Kc, first write out your equilibrium constant expression. So products over reactants. So concentration of N2 times the concentration of H2O squared because of the coefficient over the concentration of NO squared times the concentration of H2 squared. Once you write your expression, plug your numbers in. So 0.019 times 0.138 squared over 0.062 squared and 0.012 squared. Again, be careful how you put this in your calculator. Use parentheses when possible, or do the numerator separately than the denominator. And when you solve this with sig figs, we do 1,000. So our Kc is 1,000. What does that mean about what is present at equilibrium? That means we have more products present at equilibrium. If the number is greater than 1, that means we have more products at equilibrium. So as we worked through this example, if you have questions in your notes, I want you to write down the questions that you have. This chapter is where you also need to utilize your book. Know that in my classroom, I have a class set of books right underneath all of the trays in the cabinet below, but you will need to utilize your book. So read through chapter 15, look at some of these practice problems, how they explain going through the practice problems, because that will be very helpful. So the final example, example 10, says a mixture of 0.2 moles of CO2, 0.1 moles of H2, and 0.16 moles of H2O is placed in a 2-liter vessel. The following equilibrium is established at 500 Kelvin. Okay, so here is our equilibrium. Part A says calculate the initial partial pressures of CO2, H2, and H2O. B says at equilibrium, the partial pressure of H2O is 3.51 atm. Calculate equilibrium partial pressures of the other three. And then part C says calculate Kp. So first thing we have to do is calculate the initial partial pressures. So we want to calculate partial pressures of CO2, H2, and H2O. Let's think about what we're given. We're given moles, we're given volume, and we're given temperature. We have N, V, and T. What could we use to calculate partial pressures for each of these? We could use the ideal gas law for each one. So we'll do PV equals nRT for CO2, PV equals nRT for H2, PV equals nRT for H2O. So if I rearrange this equation to solve for just pressure, I get nRT over V. So we're going to do this for each gas. We'll do the first one together, and then I'm going to have you do the other two. So partial pressure of CO2 equals, so partial pressure of CO2 equals N, which is 0.2, times R, because we're in atmospheres. If you notice in part B, we're in atmospheres, so let's just keep it in ATM. So let's use 0.08206 times temperature, which is 500, all divided by my volume. So pressure of CO2, partial pressure of CO2 equals 0.2 times 0.08206, or 0.0821, times 500 divided by, so this entire amount divided by 2. Okay, be careful with your order of operations. If you put it in just like this, you're going to get something different. So do N times R times T, all in one set of parentheses, all of that divided by 2, and you should get 4.10 ATM. Okay, if you didn't get this, check how you put everything in your calculator. What I want you to do is pause the video and do H2 and O2 and come back and check your answers. So for H2, you plug in your moles, your R, your T, and your volume. You get 2.05 ATM. And your pressure of H2O, again, plug everything in, you get 3.28 ATM. So those are your initial partial pressures. Because notice it says a mixture of these amounts of moles is placed in a vessel. That's what you have initially. So then part B says at equilibrium, the partial pressure of H2O is 3.51. Calculate the partial pressures of the other ones. So the change in pressure of H2O, because H2O is a product, so you always have to look at where it is. So we end with 3.51, we start with 3.28. That means that we gained 0.23 ATM of water. So let's do our ice table or rice table, whichever you prefer. Reaction, I rewrite the reaction. I write in the initial amounts. That's what we found in part A, right? I is initial. So 4.1, 2.05, 0, and 3.28. Change. Well, we know that we gained 0.23 ATM of H2O. Because it's all a 1 to 1 to 1 to 1 ratio, it's all going to be 0.23. The only difference is your products you add to and your reactants you subtract from. So we add 0.23 ATM to our products, we subtract 0.23 ATM from our reactants, and let's find our equilibrium amounts now. So now we subtract everything for our reactants, you add for your products, and here are our equilibrium concentrations. Notice H2O is 0.35 or 3.51, which is what they tell us in part B. So now we've calculated the equilibrium partial pressures, and finally part C says calculate Kp. So first thing you want to do is write the Kp expression, products over reactants, because this is Kp, you're writing partial pressures. So Kp is equal to the partial pressure of CO times the partial pressure of H2O divided by partial pressure of CO2 times the partial pressure of H2. Okay, so write all of that out. Then plug your numbers in. Once you have that written out, plug those numbers in. Right, products over reactants. And you should get 0.11. Again, you should get 0.11. So check your math. Do all of the math. Make sure that you understand how to plug this into your calculator, how to solve for all of these different things. If you have questions, write questions down in your notes, and we'll go through any questions that you have tomorrow. But these are the examples that go through the first two videos. So writing equilibrium expressions, calculating equilibrium concentrations or pressures, using an ice table, and then actually using that information to solve for an equilibrium constant.